Okay, so just so just so we all know, the talk today is going to be recorded and then uploaded to YouTube. Yeah, if you have any questions and you don't want to be recorded, send a message to me. I'll pause the recording and yeah, we'll go from there. Okay, so it's a great pleasure this week to introduce Vit Tuček today, who's going to be speaking in our seminar on BGG sequences.
Thank you. So I have a obligatory slide to include that says that I'm supported from European Union and some Croatian funds and so on. So just for the record. I will be talking today about the BGG sequences. It's kind of like introductory or not very deep talk. Because I think that these things are quite interesting. They lie at the crossroad of several branches of mathematics. And given the usual audience of this seminar, I think they might be worth looking at. So one of the possible motivations is to start looking at natural invariant differential operators, natural/invariant. So natural has some formal meaning, but you know, you can either read this 600 pages book by Kolář, Michor, and Slovak, Natural Operations in Differential Geometry, or you can just start working on concrete problems. So one of the problems that one encounters in differential geometry quite early is the following one. You just take a Riemannian manifold and you consider a class of metrics where you consider two metrics to be in the same class if they differ by a multiple by a smooth everywhere positive function. And so naturally you want to look at the group of automorphisms of such a structure. So that's something like conformal group. So you want to look at vector fields that preserve your metric up to some scale, and you just rewrite this differential equation as the following one. You take the Levi-Civita connection of your one of the metrics there, and the equation for x to be you know, of this form, so that the flow actually preserves this conformal class, is that you just take trace-free part of this equation. And this should be something that is conformally equivalent, right? I mean, you are looking for things that are kind of defined by the conformal structure, so the equation has to be conformally invariant. So that's one example of a natural invariant, natural differential operator. Just take trace-free part of this nabla A xb, so just symmetrize over the indices here. Another example of conformally invariant operator or natural operator on conformal manifolds is the so-called Yamabe operator. You just take Laplace-Beltrami operator and you add some scalar part. You just take a scalar curvature, you multiply it by this weird factor, and you let it act not on functions but on conformal densities of certain weight. So what it means is that when you change the metric by omega squared, you also change the function by omega to some power. And for this particular power, it turns out that actually if you recalculate your Laplace-Beltrami operator with respect to this G tilde, and you take the scalar curvature with respect to G tilde, and you multiply F with this scaling factor to this power, you obtain the same expression. So, you know, it's a bit involved calculation. You can imagine just changes of scalar curvature, changes of Laplace Beltrami operator, they kind of cancel out for some particular weight. So the reason I got interested in these things came from representation theory, because this notion of naturality kind of restricts to notion of invariance. So if you are on some homogeneous manifold, then natural operators are invariant with respect to your group. And of course, kernel of invariant operator is a representation of the group. And so in this way, if you know some nice invariant differential operators, you can construct some maybe interesting representations. So for the Yamabe operator, your representation is infinite dimensional, but actually for some signatures, for the Lorentzian signature, it's a unitary representation, which is quite rare. For the first example, these conformal killing vector fields, as they are called, the dimension is actually bounded from above. So the dimension of the kernel is bounded by this expression, which is just the dimension of the automorphism group. And this bound is true for any, however small, open set. So this is a very strongly overdetermined system of equations. And these BGG sequences, what they do is, originally they work just for these types of natural operators that are strongly overdetermined, and they give you a sequence, a continuation of this first operator that takes just trace-free part of this. So they give you a whole sequence of operators, which sometimes form complexes, and basically you are then looking at some generalization of let's say Dolbeault resolution or something like that. Yeah, okay, I just said that. The maximum is attained just at the homogeneous space. But the situation is quite complicated in general because, for example, the third power of the Laplace-Beltrami operator, it doesn't have any lower order corrections so that you would obtain some natural operator on conformal manifolds. So there are some weird phenomena appearing, and these BGG sequences, they give you a lot, but they don't give you everything. That's one caveat. So so what we will see today in this talk is a short, like brief introduction to Cartan geometries, and then construction of these BGG sequences of differential operators that actually uses homotopy transfer from purely algebraic representation theoretical data. So what is Cartan geometry? So Cartan geometry, this is the definition I like the most. So you always have some model. So the model space is G mod P, or rather a pre-principal bundle G over G mod P. So Cartan geometry is arbitrary P-principal bundle with a choice of so-called Cartan connection. So Cartan connection is one form on this total space of the principal bundle valued in the Lie algebra of your group G that satisfies some conditions. So these conditions might seem weird at first, but what they are really saying is that you just look at this homogeneous case, G over G mod P, and there, on any Lie group, there is a left invariant form called Maurer-Cartan form. So for matrix Lie groups, it can be given by expression, by the following expression. There is a general definition for any Lie group just using left translations. So you just look at this homogeneous case, and then you decide, okay, let's replace this Lie group G by a general principal P bundle, and let's just see what properties of Maurer-Cartan form I can keep. And these are the properties. So you have some kind of invariance with respect to right translations. This second property is, so for homogeneous case, this second property holds for all elements of the algebra G. What this is, this x psi, this is the fundamental vector field. So you have a P principal bundle, so each fiber is diffeomorphic to P, and so if you pick a direction in P, you can just exponentiate it to a vector field. Sorry, you can just define a vector field using this action on the fiber. So this vector field is kind of in the fiber-wise directions, and this just says that if you stack it into this one form, you get the original starting vector for this vector field. So it just reproduces the vectors of fundamental vector fields for the P directions. So in the homogeneous case, you would also have this for G, like the rest of the directions from that are there in the whole G, but now that doesn't make sense anymore. But what makes sense is to demand that omega is still linear isomorphism between the tangent space of the total space and the algebra G. So this is a Cartan geometry, and then you can define curvature just as you would by Maurer-Cartan equation. So for the homogeneous case, there is this famous Maurer-Cartan equation that says that this expression d omega plus 1/2 of bracket of omega with itself is 0, and in general there is no reason for it to be 0. So you just define curvature by this, and of course you want to capture quite general geometrical phenomena, and then there is often some torsion involved, and that's the case here as well. So the torsion of a Cartan geometry is defined as the image of this curvature under the canonical projection from G to G mod P. Yeah, so there is another description of Cartan geometries, a local picture or a gauge picture. So you define Cartan gauge as some open, so you take an open subset of your manifold, and you take G, the algebra G valued function on this open set, and you just demand that this satisfies the so-called regularity condition, that when you compose it with this canonical projection, oh sorry, this should be P here, it should be G mod H but G mod P, so that this composition is linear isomorphism. So this is a Cartan gauge, and then Cartan atlas is a set of Cartan gauges such that you actually cover your manifold, and that when you have two different gauges, then at the intersection you have a smooth map into the Lie group P, such that the following formula holds. So you have some kind of gauge equivalence, and from this you can actually build this P principal bundle and so on. So these descriptions are equivalent. Maybe it's worth mentioning that if you consider this K to be constant function, then you obtain something which is called, I think, GP structures, or maybe just P structures. So these appear in the work of William Goldman and people who are doing geometrical structures on Riemann surfaces and stuff like that. So that's a local description for Cartan geometries. And here are some examples. I should also say what is the morphism of the categories. I just told you what are the objects. So morphisms are kind of obvious.
Sorry, this theta, that's a function or a one form?
Sorry? Theta?
It's a function or one form?
It's a one form, sorry. There are quite a few typos here. I didn't have time to go through my slides properly. Yeah, so theta is a one form, I think. Yeah. So from this global definition, it's easy to say what would be the morphisms, right? It would be just the morphisms of P principal bundles that respect these Cartan connections. So pullback of one Cartan connection is the other Cartan connection. So it's basically just local diffeomorphisms that respect these geometrical structures. So there are some general results that say that the category of Riemannian manifolds that has Riemannian manifolds as objects and local isometries as morphisms is equivalent to category of Cartan geometries modeled on this pair. So you have just Euclidean, sorry, this should be N here, just Euclidean motions in Rn, and you take a point. So the fixed, the isotropic group of a point is isomorphic to SON, and so Euclidean space as a Klein geometry, we can say is just the homogeneous space of Euclidean group mod out by the special orthogonal group. And if you take a category of Cartan geometries modeled on this pair, then it is equivalent to category of Riemannian manifolds, but you have to also include some conditions on this Cartan geometrical side. So you always have to have some normalization. So think of think of Levi-Civita connection, right? So if you have Riemannian manifold, you have plenty of you have infinitely many affine connections that preserve the metric tensor. But if you demand that the connection that preserves the metric tensor is torsion-free, then there is a unique one. So something similar works here at this Cartan geometry side. You always need some normalization. So usually the statement is that category of torsion-free Cartan geometry is such that, and then there is some algebraic condition on some kind of homogeneity or some kind of algebraic equations being satisfied and so on. But some further examples include conformal structures and projective structures and many more. So, for example, these conformal structures, they take conformal manifold the way I defined it at the beginning, with these conformal classes, and then the category of conformal manifolds, with local conformal, I don't know how to call it, isomorphisms, is equivalent to Cartan geometries modeled on this pair. So you take SO group of appropriate signature and mod out by a certain semi-direct product. And here you have some normalization. So you have to take torsion-free regular Cartan geometries of this type. So I will not go into details, but just as a side note that there needs to be some kind of normalization. Another example, which is quite classical, is example of projective structures. So you take a manifold and a class of affine connections, and you say that you define two connections to be in the same class if they have the same unparameterized geodesics. So classically, like classical projective geometry as a Klein geometry, as a homogeneous space, would be a study of lines. So you kind of generalize that to geodesics of some affine connections. And it turns out that this is equivalent, again, up to some normalizations to Cartan geometry modeled on this pair. So you have, again, a simple Lie group and some semi-direct product. Then there are much more examples like Grassmannian geometries, CR geometries, these famous Cartan 235 distributions, contact structures, and so on. And all these examples, except for the first one, fall into the class of so-called parabolic geometries, which are Cartan geometries modeled on a pair of a semi-simple Lie group, such as SO, SL, or their products, and a so-called parabolic subgroup, which is always a semi-direct product of some semi-simple group and some in general nilpotent subgroup. So in this case, these nilpotent subgroups are actually abelian. But for contact structures, you, for example, get the Heisenberg subgroup as the second factor here. So maybe we should look more closely at this Riemannian case to see how it actually works. So the Lie algebra of, again, there should be just n Euclidean group on Rn. The Lie algebra of G can be given by matrices of this form, right? You look at the affine group on Rn, and you realize this affine group by these matrices. There is this trick just to extend the matrices to one dimension higher, so then everything can be given by matrix multiplication. And but you want not general affine group, but Euclidean motions. So you restrict this lower right term from GL to SO. Sorry. So this is the form of the Lie algebra. And what was this Cartan connection? So it was a one-form valued in this Lie algebra. So you can just project onto these two parts. So I just call them omega Rn and omega SO. And then actually it turns out that omega Rn is the so-called soldering form. And this omega SO is actually given by the Levi-Civita connection. So how does it work actually? So if you take a Riemannian manifold, just pick some orthonormal frame, EI, and then using the metric, you have a dual coframe theta I, and then there is this famous Cartan lemma from linear or multilinear algebra that says that there exists a unique set of one forms denoted by theta ij, which are actually anti-symmetric in the indices, such that d theta I is theta ij wedged theta j. And so this coframe gives you this soldering part, and this theta ij coming from Cartan lemma give you this SO part, because you just identify SO with anti-symmetric matrices. And it actually, in fact, if you take Lebesgue-Civita connection of this Riemannian manifold, this theta ij are given by the Lebesgue-Civita connection. So this is how you define this Cartan gauge, because in general you can take just locally these orthogonal frames only locally. This is how we define Cartan gauge, and then you have that's one of the equivalent descriptions of Cartan geometry. But somewhere here is hidden this normalization, right? This torsion freeness. Okay. So going back to the global picture, once you have this Cartan geometry and some module for the group that's acting here on this principal bundle, you can form associated bundle, and this Cartan connection omega defines in a natural way affine connection on this bundle, on this associated bundle. And once you have a connection on a vector bundle, you can just extend it to so-called twisted de Rham operator. So you just take the formula for the de Rham operator, and wherever you see differentiation of a function by a vector field, now we are not trying to act with this operator on functions, but on the sections of vector bundle. So instead of differentiating a function by a vector field, you just take this this connection that you have on the vector bundle, and you act on the section. And that's the definition. But you can figure out a formula that looks like this. So epsilons are just sections of the forms, and locally the formula for this twisted de Rham looks like this. And you see you have some curvature terms. So kappa is something called curvature function, which is just given by this curvature of nabla. And then you have the nabla itself, but you also have this very important part, which is just algebraic, which is given by some algebraic operators. So this partial delta is a Lie algebra cohomology differential. So you just should be more specific here. You look at the Chevalier-Eilenberg cohomology. Okay, so this is already specific to the parabolic case. Sorry. So in the so we will come to that later. So sorry. So anyway, you just obtain this twisted de Rham sequence, but it is no longer a complex, because this nabla doesn't have to square to 0, right? This nabla just squares to the curvature of nabla. I mean, this d omega squared is just action of curvature of nabla omega on the sections. So you see, whether we have a complex or not, or maybe some subcomplex here, if we restrict sections to some subspaces, this is all determined by curvature. So in particular, if our Cartan geometry is flat, if we are in the homogeneous case or some open subset of the homogeneous case, we get a complex. And now something which should be familiar to most of you guys is this nice observation by Stuart Armstrong. So you consider the inverse of omega as a mapping from the total space of the bundle times the Lie algebra into the tangent space of the bundle, right? It's a one form, so it's a mapping from tangent space here. Also, if you consider the inverse, it's easy to see that it is actually P equivariant, and so it factors to this isomorphism. So here for a P module V, I'm just taking the Lie algebra itself. And this little observation tells us that then this associated bundle is actually the entire algebroid of the principal bundle of the Cartan geometry. And so this actually has a special name, and it's so-called adjoint tractor bundle of a Cartan geometry. And Stuart Armstrong observed that if you take this parabolic case where G is semisimple and P a parabolic subgroup, one can define a pre-Courant bracket on this entire algebroid, on this adjoint tractor bundle. The formula is a bit involved, so just to give you a flavor, if you have a semisimple Lie group, then on the Lie algebra you have a non-degenerate killing form that gives you the non-degenerate scalar pairing that you need to have on a Courant algebroid, and then that's this B, that's the killing form, and then you just play with the connection given by the Cartan connection, and with this part, this bracket with index little g, is just the Lie bracket, right? So it's a combination of basically all the ingredients that you have, which is a bit non-trivial, but it gives you nice pre-Courant structure on this adjoint tractor bundle.
Vit, why is it a pre-Courant bracket? Like, why not a Courant bracket?
Because the Jacobiator, so this is the non-symmetric bracket, the non-anti-symmetric bracket.
Yep.
And
okay.
And one of the then one of the things you want is that this like if you take bracket of x with bracket of yz, that you have Leibniz rule basically, and
Yep.
then this is violated in general. So you need to have some 4 form 0. Basically, you take the Jacobiator of this bracket, and the result says that it is a 4 form, and when this 4 form is 0, then you have a Courant algebroid. So, and it's not, it's called pre-Courant algebroid by Weissmann.
Okay. Okay.
So it's I
does
think
it
this
does it
form
have to be 0, or could it be just exact, like Jacobiator being d of something?
I think 0 because then it's reformulated as saying that some Pontryagin class vanishes. So
Yeah. Okay. Cool.
okay. So that's more or less it for the Cartan geometry part. So if you have any questions, ask them now.
Sorry, what is the base of AM? It's just M?
Yes, M. Everything happens over M.
And,
so we are just,
and what is the anchor then?
So in general,
sorry.
So yeah, the anchor, you just take the projection from G, from Lie algebra G, to yeah, okay. You know what? Maybe I should. This is actually a place where I wanted to switch to another app. Let's see. There is a whiteboard actually, so maybe we can try to use that. So.
I mean, isn't it just the push forward with the projection of the principal bundle?
Push forward of the yes. So the tangent bundle to M is this. Just take the canonical projection from the Lie algebra G to G mod P, and the associated bundle to that is the tangent bundle.
Okay, thank you.
And yeah, I should have said that this oh god, yeah. Oops. No, maybe this adjoint tractor bundle is not exact, but it is transitive. So you know, it's T star M plus something plus Tm, morally speaking. So this splitting might not be equivariant, but there is a short exact sequence, you know, of this form. Yeah. So maybe that I should. So this is what I mean really. So this adjoint tractor bundle sits in a exact sequence of this form. Okay. Okay, so now comes the algebraic part, for which I need some, yeah, this will be a bit technical, but I think it's a good idea to just give you some crash course on parabolic subgroups. So
can I ask one more question?
Sure.
So you said that it's important that P is parabolic in that pre-Courant algebroid structure. But in Euclidean example, SON is not parabolic in ISON, is it? What goes wrong in there? Can you still construct adjoint tractors or in that example and
you can always say construct adjoint tractors. Not quite sure what's the result on pre-Courant structure there. So you have the Lie brackets, you have the connection. I think you have all the ingredients, but I actually never checked what you get when you try to just play with the bracket for the, let's say, Riemannian case. So that's a very good question. Thank you. Thanks. Yeah. So I just mentioned the result of Stewart Armstrong and Rongmen-Lu that says that in this parabolic case you get pre-Courant structure, and then you have all these you know, corollaries like this vanishing of Pontryagin class and so on. But I actually never checked what this definition gives you for these reductive cases like Riemannian structures and so on.
I see.
It might be worth looking at. Yeah.
Okay, thank you.
Welcome. Okay, so what is a parabolic subgroup? So the definition actually comes from some algebraic geometry, but yeah, maybe it's just easiest to say what is a parabolic subalgebra, and then basically you just get everything by, you know, exponentiation and you know, taking Lie groups with these Lie algebras and so on. So of course there are some technical details and issues in the real case, because you have many different groups and some, you know, discrete coverings and so on. But let's put that aside and just say what is a parabolic subalgebra. And you know, you have a G semisimple, which means that you can pick a Cartan subalgebra. So G is semisimple. And then there is this whole nice structure theory that starts with picking maximal commutative subalgebra, this Cartan subalgebra. And again, there are some issues in the real case because not all of them are conjugated, but let's say let's do everything over complex numbers, then all the Cartan subalgebras are conjugated. And you can pick a set of positive roots. If you don't know what it is, doesn't matter, because this is actually equivalent to picking a triangular structure. How is it called sometimes? What it means is that that basically it gives you splitting of G into something called n minus plus H plus n plus, this structure. And so you realize this Cartan subalgebra as a diagonal, basically in basis adapted to this splitting, and these ends will be just lower and upper triangular algebras. And so H plus N plus, sorry, right? H plus N plus is so-called Borel subgroup. And then whatever is between this Borel subgroup and G is parabolic. And it leads to similar decompositions. So basically you have something called U minus, L, and U plus. And in a basis adapted to this splitting, your matrices look like this. So you have, you have a block diagonal subalgebra L. And then you have this U plus and U minus. It's like block triangular. So in the maybe I should really erase this now. Yeah, great. So if I suggestively just like draw all the blocks that are there. So here you can see that actually U plus is not so okay. So it's upper block triangular. So in particular, it's nilpotent. But moreover, there is a grading. You see that this is something like let's call it G1. So matrix is just with entries in these three parts G1. And if you just take the anti-commutator, sorry, the commutator of these matrices, you get something which is here, right? So you have some G2 and G3. So what I've drawn here is a case where you have this U plus with this grading G1, G2, G3, and this is actually the case in general. So another nice way to define parabolic subalgebra is to get a grading, or to have a grading which is symmetric. So this is this U minus, and G0 will be this L, which is sometimes called Levy part, and then you have these positive guys, U plus. And actually, the killing form of G always works just by non-degenerately pairing these things, right? So B restricted to U plus or U minus is identically 0, but it pairs non-degenerately minus I and I. Yeah. So this nice decompositions also respect the killing form. Okay, so any questions here for parabolic subgroups, subalgebras? No. Thank you, Jan, that you are the only one that's keeping the video alive, because I can actually see people, nodding or Great. So I'll switch back to the presentation. So what we want to do now is basically we want to look at this twisted de Rham sequence and kind of reduce it to a sequence of operators which might be of higher order, but which will act on bundles of much lower rank. And the reason to do that is that you just obtain an interesting sequence, and if you do it as I will show you by homotopy transfer, then whenever this twisted theorem is a complex, of course the transferred sequence will be also a complex, calculating the same cohomology, right? So you will obtain a sequence of some higher order differential operators that calculate the same cohomology as twisted theorem complex, and by some abstract theorem that calculates the sheaf cohomology with values in the fiber.
But Vit, did you say that it only gave you a cohomology if it was flat?
Yes, but well, no, it's the other implication. If it's flat, then it's a complex.
Right. Right. Okay.
But
sorry.
you can imagine that you take a very small representation. Where is it? You take very small representation. Let's say you take one-dimensional representation.
Okay.
And there is no curvature there. Or there might
Sure.
not be any curvature there.
Yep.
And so you obtain a complex, or maybe you just obtain a subcomplex. That you take some subbundles here, and on those subbundles the curvature acts by 0.
Mm-hmm.
Or you can take not a general manifold, but maybe manifold, I don't know, for which some parts of curvature vanish, which is Weil flat or a Ricci flat, and then maybe you get a complex.
Okay. Sure.
So, okay. So now we are just looking at cochain spaces for Lie, Chevalley-Eilenberg, Lie algebra cohomology. Okay, I'm sorry, I switched notation again. So what was U plus and U minus is now P minus and P plus. Sorry. So anyway, these cochain spaces, they are defined as just linear homomorphisms from the wedge of P minus. So if you are calculating cohomology of the algebra P minus with values in some module, you take linear mappings from the wedge of P minus into the module. And there is this natural isomorphism from the wedge of P minus dual tensor with the module. And as I mentioned just a little while ago, the killing form pairs everything what is in P minus non-degenerately with something in P plus. So this P minus dual is actually P plus. And so this cochain space for Chevalley-Eilenberg cohomology of P minus is naturally isomorphic using this killing form to wedge of P plus tensored with V. And that's actually the chain space for Chevalley-Eilenberg homology of P plus with values in V. So, suddenly you are looking at one vector space, let's say this one, the chain space, and you have two differentials there, but of different degree, right? You have one differential from the Chevalley-Eilenberg homology, and then you have the differential from the cohomology. So this is how it looks like. This delta, or this partial up there, is the cohomology differential, which raises the degree. And this delta down here is the homology differential, which lowers the degree. So these are the formulas. This partial for the cohomology, it really looks like theorem, So okay, in coordinates it looks like this, but this is maybe not so familiar because it acts on these wedges of P plus, but on this space of homomorphisms, it really behaves like the classical theorem. Just instead of forms, you just take everything over a point basically. That the formula is the same as for theorem. So if you just transport this operator over the isomorphism, you get this. The homology differential is kind of dual to that. So you take out one of the guys in the wedge and you act with it on your coefficient V. And then you take out two of them and that's it. So what we have here is that these guys are actually invariant with respect to some algebras or groups. So the homology differential is invariant with respect to K plus P plus, or sorry, this should be L plus P plus, and the other one is invariant with respect to the opposite opposite subgroup. So it's again just the diagonal acts on both of them in the same way. So they are always invariant with respect to L, but one of them is invariant with respect to P plus, the other one with respect to P minus. Why is this important? It is important because let's say we want to use this differential to build some subbundles. You know, just right. So I mentioned that the tangent space is isomorphic to bundle associated to G mod P. Right. So G mod P is P minus. It's isomorphic to P minus. Right. That just follows from the triangular decomposition. And P minus is dual to P plus. So bundle isomorphic to P plus is the cotangent bundle, right? So that's why I'm actually looking at this chain space, because what I have here is a space whose associated bundle is the forms, the exterior forms valued in the associated bundle to V, right? So that's will create my twisted Deram sequence bundles. But this the algebra cohomology differential is not well defined there because it is not P invariant. So P is L plus P plus. Yeah? That's how I chose P. But I should have also mentioned it before. So what I'm saying here is that P is L plus P plus. So of course P plus is a representation of P. So all these spaces, these just ith wedge of P plus, that's at V, are representations of P. So you can form associated bundles. But to form a subbundle of closed or co-closed guys, you need operator which is invariant with respect to P. So you can only look at the homology. So what to do with cohomology? Again, just a small reminder. I have shown you this formula for twisted Deram, which contains this operator inside. But we have to stay in this algebraic world for a little while longer. So you have two operators of different degrees. So what you do is you sum them and you square them. So this is some kind of Laplacian, right? I mean, this is basically imitating Hodge decomposition. So what Hodge decomposition means is that you try to decompose this chain space into the kernel of this Laplacian and images or image spaces of these two operators. So Hodge decomposition means that you have such a decomposition where the kernel splits as image plus the kernel of Laplacian, kernel of the other splits as the image of the other plus kernel of the Laplacian. And so basically what this says abstractly is that the kernel of this algebraic Laplacian gives you unique or preferred representatives, like let's say harmonic, algebraically harmonic representatives in the cohomology or homology classes. And this decomposition works whenever these two operators are so disjoint, meaning that the intersection of their kernel and image is trivial. So if you manage to find some good positive definite or negative definite inner product on your chain space, or then if it's invariant, then you actually have that these two differentials are adjoint to each other, or maybe up to some constant. So this was done. This invariant definite inner product was found by Kostant for any finite dimensional representation of G, not of P, but of G, and it was this kind of given by definition for irreducible unitarizable modules of any dimension. But yeah, let's leave that aside. So by this result of Kostant, we actually have this Hodge decomposition. So we have some canonical preference for these homology classes. And moreover, Kostant also gave a formula for these homologies or cohomologies. This is the result. Once you have chosen your Cartan subgroup and these positive roots or this triangular decomposition, you have a so-called Weil group, which is a finite group of Coxeter type, which is generated by root reflections, whatever that means. And this finite group has a subgroup that corresponds to this subgroup L of P. And so you can kind of take any element of this Weil group, of this finite group, and write this element as a product of two so-called minimal length representatives. One of the representative will be the representative of the coset of, and the other one will be in the subgroup. Well, anyway, what this is saying is that these homologies or cohomologies are just calculated abstractly using this highest weight theory for notation, for identifying irreducible representations like this. So this is that there is some combinatorics, there is some formula that gives you the homology bundles that will appear. So how do you transport this twisted theorem to these? Okay, so maybe first a recap. So what are we doing is that first you find some nice inner product of these cochain spaces. Then you take the differentials, you define the Laplace, you get the Hodge decomposition, and then you can actually write down the projector. So this is very simple. You take any element in the cochain space, and if it's in the kernel, it spits it out. If it's not in the kernel, it gets killed, right? And you can actually write this just because you have this Hodge decomposition, just because actually the image of this algebraic Laplacian is image of these two differentials, right? So this is still part of this. It's not written explicitly here. No, it is. It's here. Image of the Laplacian is the sum of the images. So kernel and image of this Laplacian intersects just at 0. So you can actually write the projector like this. The problem is that this projector is not P invariant, so it won't give you a well-defined operator on these bundles, because we have to associate these operators to P representations, and when this is not P invariant, it's not well defined, right? So the solution is to, pass from bundles to sections of bundles and to add some differential terms which will fix the invariance. So this is what we do. We just expand the definition of this algebraic Laplacian, and then it's easy to see that this Laplacian actually commutes with delta inverse. So you can rewrite it like this, and this is what you do. You just pass from a representation, to a bundle. You pass from this the algebra cohomology differential, which is messing up your P invariance, to this twisted theorem, which includes it. So you just basically add some curvature terms and differentiation terms using this Cartan connection. You pass from algebraic Laplace operator to something which is using just P invariant operators, which are well defined on these sections. And then you have this problem. You need to rewrite this Laplace inverse delta as something. You need to have this. So we are looking for inverse of this differential operator of first order on the image of this algebraic Lie algebra homology applied to sections of your bundles. And if this actually exists, then you just define, in analogy with the projector in the algebraic case, you define the projector on the sections like this, and it's a differential operator of, well, okay, a priori it's not clear, right? So d omega is a differential operator of first order, but who knows what this q is. But the claim is that if you do this, if this works, you basically have homotopy transfer data from this twisted theorem sequence to a sequence of homology bundles, to a sequence of bundles which are associated to real algebra homology. And okay, we are supposed to finish at 3, Mark.
Yes, but we started a little bit late. So
okay.
Let's say 10 past. So let's say another 7 minutes.
Okay, so maybe then I will just show you how to do this inverse. So for finite rank bundles, it's easy. You can actually rewrite this differential operator as the algebraic operator plus some perturbation, or minus some perturbation. And this perturbation looks like this. Turns out that there is a very simple formula for that. It's really just this affine connection, this so-called tractor connection there, followed by a wedge of this epsilon. So epsilon is a section of these forms. And since you have this grading on G, it gives you grading on any representation. And P was basically G0 plus G1 plus G2 plus up to Gk. So if you restrict to action of P, you just need to take care. You see that P actually, it can only raise your grading up, right? It cannot move it down. And since epsilon is a section of the forms, and the forms are associated to P plus, this actually raises the degree by 1, right? So this perturbation to this algebraic guy actually raises your naturally defined degree on your bundles by 1. And what that means is that the Neumann series for this guy are actually finite, right? So you have a finite rank bundle. This finite rank bundle is filtered by subbundles, and P is moving the subbundles. P plus are moving the subbundles up by 1. Yeah, I should have really included some explicit example for this. Sorry. Yeah. So maybe again just switch to whiteboard. Does it work? What I'm saying is that sections of your bundle are naturally filtered So you have, so these are the sections of V, and then you have a subbundle formed of sections of, and sections of the subbundle. So let's say V1, and then you have some further subbundle, V2, and so on. And what this action of E plus is doing is that it's shifting it down by 1. There might be, subbundles at the same level, so several of them, like this can split into, V1, 1, V1, 2, and so on. But, what I'm saying is that the structure of this representation V might be quite complicated when you look at it as P plus representation. But whatever happens is it's naturally filtered or graded, and P plus shifts this grading. And so if we have a P plus term in this, in this operator, some power of this operator will eventually have to be 0, because it will just move the grade to grade 100, and we have just 5 rank bundles, so there is no room for that. So you can actually get the inverse as a finite Neumann series, and you see this n was an operator of first order. So basically, this is algebraic. So basically, this operator is of order, how many subbundles you have there. How long does it take for P plus to kill everything in the subbundle? So this homotopy transfer data then is operator of arbitrarily high order depending on the rank of your bundle. And the rest is just just playing with formulas and nice little calculus. So you just define that this generalized projection operator behaves in a nice way, that, you know, when you compose it with homology differential, it gives you 0. So it actually induces identity. It actually induces identity on these bundles associated to homology representations. You can calculate that the commutator of this twisted DRAM and this projection operator is given by curvature and this Q operator that I have just defined using this inverse. And for k equals 0, the operator is always a projection. In the flat case, it's always a projection. In general, when you square it, it's not a projection. There is again some differential operator of high order, curvature, again differential operator of higher order, and so on. So you can, you know, figure out a lot of formulas, but what it basically says that you have a chain map. It's a bit weird to phrase it, right? Because the twisted DRAM sequence is not, in general, not a complex, but when it is, this defines then a chain map which is homotopic to identity. This is what it says, right? So how do you define these BGG sequences? You know, you just using this commutative diagram. So you start in some homology bundle. Operator giving conformal killing vector fields, it's bounded by this, what was it, n+2 times n+1 over 2. Well, conformal killing vector fields should be something like infinitesimal automorphisms of the structure, right? So actually the bound, the claim here is that when you take this adjoint tractor bundle, this bundle associated to Lie algebra G, in this conformal situation, and you know, go on with this procedure of constructing BGG operators, the operator you obtain is exactly this conformal killing vector field operator. And then the corollary says that actually the kernel of this operator is isomorphic explicitly using these projections to kernel of the adjoint kernel of the connection on the adjoint tractor bundle. But kernels of connections are easy, right? It's basically given by holonomy, and in the flat case, and on sufficiently small open set, you get that the kernel is in one-to-one correspondence to points in the fiber, right? So you can pick any point in the fiber and you just parallel transport it to the neighborhood, and if the neighborhood is simply connected, you have a well-defined section. Well, if there is no holonomy on this neighborhood, then you have a well-defined section, and so you have a well-defined solution of this operator, and vice versa, actually. So when the twisted DRAM sequence is a complex, then the sequence of these BGG operators is locally exact and computes the cohomology of M with values in the locally constant sheaf of parallel sections of V. So you know, just take locally constant sheaf of this blackboard V. And in general, when it's so this correspondence works in the flat case, but in general you have to include some lower order terms, but the conclusion is still true. You just modify this connection by some scalar term, basically. But since you have homotopy transfer data, you can actually do much more. I mean, this construction is natural. It just uses all these ingredients that are there in a very natural way. So, for example, whenever you have some appropriately equivalent mapping between some representations, you can use wedge product on forms to define some B differential operators the following of the following form. It's very similar to how we define these BGG operators. You just again take some representatives, hit them with this generalized projection, and then apply this operator, whatever it is. So in this case, it is algebraic operator taking two sections, spitting out another one. Before it was the twisted theorem, it was just taking one section, spitting another one. You can put here whatever you want, and then you just project the result back to homology bundles, and this is well defined by differential operator. And since it's all natural, it shouldn't be that surprising that it satisfies some kind of Leibniz rules. So you see that this is a Leibniz rule up to some curvature terms. It looks like a mess, but basically you can just use this this abstract theory of deformations of algebras and rephrase everything as some through this homotopy transfer. So that kind of makes some sense of these formulae, that they are all somehow coherent, because you can just continue adding representations and mappings and so on. And so you can for example take some algebra as a bundle. So if you have an algebra which is a G representation, then this will define then like a curved version of this algebra. I mean, curved depending on which manifold you decide to do this on. If you decide to do it on a homogeneous space, it will be genuine A infinity algebra. If there will be some curvatures, then there will be some ugly terms like this. I will finish by saying that these multi-differential operators were not really exploited that much, mainly because it's actually a bit hard to do explicit calculations, right? What you need to do is you need to have operations like this explicitly. There is one article by Matthias Hammerl who's just playing with some cases in conformal geometry. So you can take let's say spinner representation and exterior forms, and you can look at what BGG operators these give you, and then you can, let's say, couple spinners to spinners and decompose it, and then project onto different parts of the decomposition and see what it gives you, and see whether these relations between all these BGG operators, so these are BGG operators corresponding to a priori different representations, what relations does it give you? And since these projections from the tensor product to some of the constituents can be quite nasty to write down algebraically, it's hard to form conclusions in like this direct, naive manner. Okay, so that's it from me. Thank you.
Okay, so if you guys want to unmute yourself, feel free to give Vit a hand. So. And are there any questions? Just unmute yourself. Don't need to raise your hand or anything.
So I think we talked about it, but do you know about how the formulas of the homological perturbation lemma come here, or I just didn't? Are they there?
It's a bit hard to formulate. So yeah, that's what I was trying to explain in the end. So if you take, yeah, so let's say here, let's say that W1, W2, and V are all the same thing, and it's an algebra, associated algebra, which is also a G representation. Then what this gives you is A infinity structure. Right? Because you can take more copies of A and you obtain 3 differential, 4 differential operators and so on. And to see that there are some relations between these operators, like this is an operator of arity 1, this is a bidifferential operator of arity 2, with A going to A, you will have a 3 differential operator of arity 3. And there are a lot of relations between them, and they are actually the A infinity relations. And the easiest way to prove it is to just show that this is all given by this codifferential on the dual cotensor coalgebra. You know what I mean?
Okay, and so this mu, you would really turn it into a differential on the Chevalier-Eilenberg complex.
This mu?
Yeah, or no?
No. But
Okay.
what you do is yeah, sorry, it's actually missing here. Sorry. Yeah. Yeah, sorry. I'm sorry. I didn't have time to prepare my slides. So what you do is you take the homology bundles for these representations, and then for 2 sections, let's say alpha and beta of these homology bundles, you take this generalized projection. It's basically given by this homotopy transfer, and that will land in sections of bundle associated to W1 and W2. Maybe I should just writing this down. Yeah. So I will just use the same bundle. So so you take pi alpha, pi beta, you hit it with this mu. Okay, so pi alpha ends up in, yeah, sorry, no. I'm a bit ahead of myself, so let's take it slower. So you take 2 sections of the homology bundles, which are associated to this representation V. Then this pi alpha lands in sections of bundle associated to V. So the values of pi alpha and pi beta are in the fiber in V. So you can hit them with mu, which goes from V. V. So this is again a section of the bundle associated to V, and so you can hit it again with this pi, maybe projection to homology, this mu. And that's in.
Okay, so you use like the explicit formula for these massive products and stuff.
Yes.
Okay, and this pi, maybe Branja will know. So this pi is like that perturb inclusion or something.
Yeah. So pi is the chain map. No, I don't know. So it's this guy. Yeah, maybe I should switch back to the presentation because it's written there.
So it's really the.
Where is it? Here.
Yeah. Okay.
Yeah.
And Q is made out of the inverse of this delta D plus D.
Yes. Okay. It's really, you just look at the projection to harmonic forms in the algebraic setting. You rewrite it a little bit, and then you kind of identify these 2 guys and name them Q, and you try to kind of move it to this bundle side.
But why does this pi go from homology to the original sections?
So, okay, strictly speaking, it does not. It just goes, it's an operator from V to V, or let's say from forms with values in V to the same space. But this lemma, or this proposition, says that it actually defines, it vanishes on the image of delta and maps into kernel of delta. And since delta was P invariant, kernel of delta is actually a subbundle because it's defined by P invariant operator, so it gives you a subbundle. So it actually, it induces identity on the homology bundles. So to be formally correct, you have to include this, like taking a representative or projecting to homology or something like that.
Okay, no, that's fine. Okay, thank you very much. I will not
Welcome.
take others' time.
Okay, if there are any other questions? Okay, no, it doesn't seem like it. Okay, so let's thank Vit again, and
Thank you.